These are the computed problems continued for the chapter on motion. So here's number 8. Apparently about a car. A car travels along a certain road at an average speed of 40 kilometers an hour and returns along the same road at an average speed of 60 kilometers an hour. Calculate the average speed for the round trip. And then it says in parentheses, don't say 50 kilometers an hour. So it goes a certain distance at 40 kilometers an hour. By the way, that's 25 miles per hour. And then on the way back, same distance, except they don't tell us what the distance is. It's 60 kilometers an hour. And that would be in the neighborhood of, a little less than 40 miles per hour. So it's definitely not a race car, but I figured I'd just choose this one here. Okay, notice yet they don't give us what the distance is. So I put a question mark there, but they're asking us to figure out what the average velocity is. So average v equals, and that's actually what they want us to figure out. And actually I'm just going to use this one here to highlight that. Well, in that case, what I do like to do is actually use a token distance, or just one that I make up, that helps me to figure out this problem. And the distance that I like to make up is 200, whoops, I meant to use a different color, 240 kilometers. Why? Because both the 40 and the 60 divide easily. So on the D equals 240 kilometers, on the way there, that would mean that the time is that it takes is 240 kilometers divided by 40 kilometers an hour. Of course, we can do that in our heads too. That takes 6 hours. On the return trip, that's 240 kilometers divided by 60 kilometers an hour. That's 4 hours. And then, of course, the kilometers divide each other, and that hour that's in the denominator of the denominator goes to the numerator, which also makes sense when we look at time. We need to have that time unit in the numerator. So 6 hours and 4 hours, that means that the total time is 10 hours. And the total distance is, of course, to get there and return, so that's 480 kilometers. And that means that the average velocity is 480 kilometers divided by 10 hours, and that comes out to 48 kilometers an hour. That seems a little surprising. Of course, they warned us in the problem here, but the main reason mathematically why it's not the exact middle between 40 and 60, which would be 50, but something else, in this case 48, is that the 40 and the 60 appear in the denominator, and because of that, the average is not going to be the arithmetic average, which would mean 50, but different. Problem 9, which says, if there were no air drag, how fast would drops fall from a cloud 1 kilometer above the Earth's surface? So I guess call this number 9 and drops. And we have a distance of d equals 1 kilometer. And that says in parentheses, let that air raindrops experience air drag and fall. Okay, so we have d equals 1 kilometer, or 1,000 meters. And then they're asking for v equals question mark. And then it turns out that each equation that we encounter in this chapter has to contain time, and we don't have time given here, so we can't right away determine velocity. We actually have to determine time first and then do something with that. So that's what we're going to do. And there is the straightforward equation for free fall that says distance equals 1/2 times gt squared. And plug in the numbers of 1,000 meters equals 1/2 times 10 meters per second squared times time squared. And here we solve for time arithmetically. And the algebra for that equation is already done in the chapter. It's t equals the distance times 2, so that's the 1/2 from the other side, goes to that side, divide by gravity, and of course to get, so the 10 goes down here, and then you need to get rid of the square here, so that's where the square root comes in from. And as I said, that's already given in the book. 2 times 1,000 meters divide by 10 meters per second squared. 1,000 divided by 10 is 100, times 2 is 200, square root of 200, do that on the side, you come up with 14 point something. I round it to 14. And then it's meters divides meters, and then the second squared in the numerator of the denominator appears in the numerator. Take the square root of second squared, that's just seconds. So 14 seconds, and now we're ready to determine what the velocity is. Velocity at the end is going to be g times time without air resistance. So 10 meters per second squared times 14 seconds comes out to 140. And then one of the seconds divides, so it's 140 meters per second. And multiplied that by a conversion factor of about 2.2, going from meters per second to miles per hour, comes out to roughly 300 miles an hour. And so that's what they say. Be glad that raindrops experience air drag. Number 10. This is about an athlete. I guess kind of looks like an athlete to us. So surprisingly, very few athletes can jump more than 2 feet, which is 0.6 meters straight up. Use d equals 1/2 gt squared and solve for the time one spends moving upward in a 2-foot vertical jump. Then double it for the hang time, the time one's feet are off the ground. So we're going to start with d equals 1/2 gt squared. And solving for t is already done for us in the book. And again, it's going to be get the 1/2 to the other side, which means multiply by 2, so 2d, divide by g, so that goes to the bottom, and then take the square root on the other side, and that isolates the t. And now we're going to plug in what they gave us, 2 times 0.6 meters, divide by 10 meters per second squared, take the square root of that. Okay, 2 times 0.6 is 1.2, divide by 10 is 0.12, and now I have to take the square root of that, and the square root of 0.12 is a rounded 0.35, and now I divide the meters, the second square denominator of the denominator, go to the top, and then I take the square root of the second squared, which comes up with the correct unit, seconds. And then for the total hang time, they say double that time, so 2 times 0.35 is 0.70 seconds. And the reason is that this one here is the free fall equation, which means it's from the peak falling down, respectively symmetrically. It's on the way up the same amount of time, but because it happens twice, down and up, that's why we double that.